In this section, I'm going to talk about rectilinear erratic motion with motion graph. This is the last section of the rectilinear motion. Before I start and talk about erratic motion, just quickly review the previous session. Take a look at to the three basic kinematic equation. It tells us if the position S is the origin function of time, v as a velocity is the first derivative of function f prime, and a as an acceleration is the second derivative function f double prime. Continuous motion, it means the ST consists of only one equation, while in erratic motion, the position function is consists of multiple position equations. From the previous session, we learned when we have the xt curve, the vt curve is equal to the xt curve slope. And also when we have the vt curve, the slope of this curve is equal to, this slope is equal to at curve. Now in vice versa, when we have the AT curve, the change in velocity between T1 and T2 is equal to the area under the AT curve between T1 and T2. We got the V. Also, when we have the VT curve, the change in position between T1 and T2 is equal the area under the VT curve between T1 and T2. We got the XT curve. Let's look at some example. For example, in this equation, S equal 15t minus 150. The variable is S and T, and the unit are meter and second respectively. We can do the differentiation and find out velocity is equal ds over dt, and as a constant 15 meter per second. Acceleration is equal dv over dt. It's showing the acceleration during this time is constant and the value is 0. You can see in the graph also. Next example. This is another position function of a time. If we derivative from position, we got the graph of v versus time. We have the linear velocity. Derivative from the velocity, we got the graph of a to t. We have the constant acceleration, 2 meters per second square. Now I'm talking about erratic motion. In erratic motion, the position time cannot be fully characterized just one equation. We need to include one more equation that apply to different time period. In math, we know that we call piece function, and from calculus, we learned how to sketch the piece function. Just keep in mind, in erratic motion, all three basic kinematic equations still apply. However, when we sketch the graph for erratic motion equation, we have to aware that which period time begin and end. Let's look at this example. An object travels along a straight path. S0 and V0 is 0. Its acceleration in meter per second squared as a function of time is given. Construct its ST, VT, and AT motion graph. From time 0 to 10 seconds, A is a linear function. For the second time period, 10 to 20 seconds, we sketch the second equation that A is equal to 2.4. For the last time period, 20 to 30 seconds, we sketch the last equation, its meaning 0. For sketching the V graph, we need to use this kinematic equation, A equal dV over dt, because it provides the relation between acceleration and velocity. Okay. For the first time period is period that is 10 seconds, 0 to 10 seconds. We integrate both sides and V equals 0.2 times t squared. Just be careful. The lower limit of V is 0 because the initial velocity is 0. We have to calculate the V at the end of this period, is meaning at time t equals 10 seconds. We do the same thing for the second period time, same integration. Now look at the lower integration limit of time. From the beginning of this time period, that it is 10 seconds, and here we again integrate from the velocity at the beginning of this time period, which is velocity equal 20. Okay, we have 20 at time 10 seconds. Also, we calculate the velocity at the end of 20 seconds, and the velocity become 44 meters per second. This one is related to the 20 seconds. And similar thing for the third time period from 20 seconds to 30 seconds, same integration. Okay. This is for time 20, the velocity is 44, we found from here. Okay, watch out, integration limit and get the last equation and sketch out graph. Now the graph of velocity is complete and we can organize velocity function here as a piece function. Now we can use the st as a function by applying this kinematic equation that is related velocity to position v equal ds over dt. The procedure is similar to the previous step. For the first time period, we do the integration and we get the position s equals 0.067 t. To the third power. We sketch it and find the position at the end of time period. The position is 66.7. Is meaning at time 10 seconds. Continue for the second period. Watch out for the correct integration limit and sketch the function in our graph and find the position at the end of second period of the time, is meaning the 20 second. At 20 seconds, the position increased to 387. And lastly, for the third period, same integration. Be careful for integration limit again and get the last part of the st function and sketch it. We can calculate at the end of 30 seconds. The position has become 827 and then complete the st graph. We find 827 from this equation. Thank you for your watching.